Hello everyone, welcome to test review day 2. Our goals for today are the same as yesterday, as it is to get ready for our test on Wednesday and Thursday. All right, so today's focus is going to be on the trig graphing stuff and just one little unit circle thing that we didn't talk about yesterday. All right, so here we go. Just kind of looking at the first one, we're going to see another one of these questions. We might remember these from the earlier quizzes in the unit where we're given a unit circle and they plot a few different positions on the unit circle, right? So they represent different riders at different positions on the Screamer ride, and they give us the angles of rotation to those positions here in the problem. And our job is to take these points on the unit circle and translate them to the graph over here. Okay, so this is a sine graph, and they tell us that here in the instructions. This is a sine graph, so you have to remember that sine represents the height. So if we were looking at rider A here, which is at 60 degrees, right, we would draw the angle in, we would drop our height. We did all of this at the very beginning of the unit, and we would say, okay, well, here's the 60-degree angle. We know this is 1, and then there's an associated height over here for that particular rider. Okay, so we could find that height by going over here to the graph and saying, okay, well, here's the sine graph. If I go to 60 degrees, I go up to where the curve is, and we would plot a point right here on the graph, and we could see that the height is about 0.866, right? So this was all stuff that we did when we first plotted this sine wave, right? So this is the corresponding position of rider A on the sine wave to his position on the unit circle. Then we could do the same thing for rider B. Rider B is at 330 degrees, right? So going around the long way, that's 330 degrees. So rider B is currently below ground. So I'm going to go over here. I'm going to find rider B's corresponding position on the sine wave. So we're going to go to 330, and then we go down to the position on the curve, which is located right here. Right, and we can see that the height of the rider is at -1/2. Right, so one more, rider C is at 0 degrees. So 0 degrees would be right here. That's right where the sine wave starts. That's right where the Screamer starts. It all corresponds, right? And we would mark point C right there. Okay, it's a pretty easy problem. Just trying to link the two, the unit circle and the sine wave, to one another. Since the sine wave is built off the unit circle, we want to make sure that we understand how those two things are related to each other. All right, so let's go the other direction. This time we're given a cosine wave, right? So this is a cosine graph. Make sure you read the directions. Okay, we can see from the shape that it's a cosine wave. And we have 3 positions marked on the cosine wave here, and our job is to find the corresponding positions on the unit circle. Right? They give us the degree measures here, just in case it's hard to read from the graph. But we can see here, let's start with point A, which is located over here. Point A is at 300 degrees, right? So if I look at this point and I go straight down, I can see on the x-axis what angle A is at. And it also tells me up here that angle A, or rider A, I'm sorry, is at 300 degrees. Okay, so recall from our unit circle that the ride starts here at ground level. So this is 0 degrees over here. And then this is 90. It rotates counterclockwise. Right, so this is a good thing to do just to kind of get your bearings before you start marking points on the unit circle, right? It's just to kind of mark your major angles. So 0, 90, 180, 270. So the ride goes around this way and you make one full revolution, then you stop back here. So 0 and 360 are at the same position. Okay, so since angle A is at 300 degrees, right, we would rotate around. There's 90, 180, 270. So 300 degrees is going to be somewhere in between 270 and 360. So I'm just going to eyeball it a little bit and say, here's about where 300 degrees would be, and mark that with point A. So this would be the location of the rider A. Now we're going to do the same thing for B. So again, if I look at B, B is at 210 degrees. Again, they give us that information here, right? So we'd go 90, 180, and then this is 270, so that's too far. So 210 is somewhere over here in the third quadrant, so we're just going to eyeball it a little bit. So we'll say 210 is about right here, and we'll mark that as rider B. All right, so then we have rider C. Rider C is at 60 degrees. Okay, so 60, there's 90, so 60 is going to be probably somewhere right around here. There is rider C. Okay. So that's how we do those problems. It's just taking these points that are on the wave and finding their corresponding positions on the unit circle, or vice versa, taking a point on the unit circle and marking it on the graph. All right, so let's take a look at this problem. It says the position of a rider in the screamer is shown in the graph, and it says the horizontal distance, and that's a key piece of information right there, the horizontal distance at the rider's position is negative 0.707. So when they refer to the rider's position, they're talking about a point that's on the unit circle, and they'll usually give you a diagram demonstrating where that point is. So this is going to be the position of our rider. There's a horizontal distance and a height that is associated with this position, right? And they tell us the horizontal distance, right? So they give us this side of the triangle, right? So we now know that this is negative 0.707. And we also know that this side is 1 since it's a unit circle, all right? Don't forget that the horizontal distance, we talked about this yesterday in the review, but the horizontal distance is found using the cosine function, and cosine also represents the x-coordinate of any point on the unit circle. Okay, so we know we're going to be working with cosine because we have a horizontal distance given to us in the problem. Now, our job is to find this angle of rotation here, all right? And to find the angle of rotation, I'm first going to find this angle inside of the triangle. So I'm going to take this triangle out of the diagram, and I'm going to redraw it so I can work with it. Just like that, right? And we know this side is 1. And for now, I'm gonna forget about the negative for now. I'm just gonna say this is 0.707, and we're gonna say our mission here is just to find this angle, right? Because if I find this angle, that's the same thing as finding this angle here. And then I can use that to find the angle of rotation, okay? So we know that cosine finds this side. We want to find the angle, so we're going to have to set up an inverse trig function here. So when we go from side to angle, remember it uses an inverse trig function. If we had an angle going to side, we would just use regular old cosine. All right, so we're going to say the inverse cosine of 0.707 equals. And I'm going to grab my calculator and do this. So we've got inverse cosine. Remember, I have to hit the blue button first. So second inverse cosine, and I'm going to say 0.707. I'm going to hit enter here. And notice that we get a 45-degree angle. I know there's a little bit of rounding there, and that's just because this value is actually rounded a little bit, but we're going to say it's exactly 45 degrees. Okay. So now we know this angle is 45. Okay, so this angle here is 45 degrees. All right, and then now we can figure out the entire angle of rotation because we do know that the angle going from here to here, that's 180 degrees plus an additional 45 degrees gets us the entire angle of rotation. Okay, so we do 180 plus 45, and that gets us 225 degrees. So our angle of rotation is equal to 225. Okay, so that's how you would solve a problem like that. Again, make sure you pay attention to the wording in the problem. Think about what information they give you. Another way that we could have done this too is we could have gone to our unit circle. The unit circle is another great way to do this. So if we had gone to look at our different positions, right, this looks like the position of our rider right about here. And since this is a negative root 2 over 2, if I put the negative square root of 2 over 2 into my calculator, you would get negative 0.707. So you would recognize that this cosine value here is our horizontal distance. Then you can say, oh, well, look, the angle is 225. Right, so if we had used the unit circle to begin with, we would have just looked for that horizontal distance they gave us somewhere in the unit circle and then traced it back to its corresponding angle. Okay, also notice that there's another angle, right? There's another negative root 2 over 2 up here that gets us a different angle of rotation, right? But we know from our diagram, right? We know from our diagram that the position of the rider is down here, not up here. All right. So don't get confused on that part. All right, so let's move on. Let's do some trig graphing here. Okay, so we have a graph. Our goal is to identify the amplitude, the midline, and the period, and then write the equation. So no problem. So let's start with the midline. This is usually the key to getting all of the other information we need from the graph. So remember, to find the midline, we look at how high the graph goes. So this graph is going up to 3, and we look at how low the graph goes, and it's going to -5, right? So this is the high, this is the low, and the midline is going to go right in between those two values, right? We're looking for the midpoint between -5 and 3, right? So if I count up, that's 1, 2, 3, 4, 5, 6, 7, 8. So I need to count up 4 to go halfway. 1, 2, 3, 4. Right, so here's my midline. And I'm going to jot that down here. So I'm going to say the midline is at y equals -1. And once we have the midline, we can determine whether or not it's sine or cosine, because I can go to 0, right? So here's x equals 0. And I would look at the midline and ask myself, does it start on the midline or does it start above or below? This one is starting on the midline, so this is a sine function. Okay? And we know that we talked about those properties in previous lessons, all right? So if it starts above or below the midline, it's a cosine. If it starts on, it's a sine. Then we want to know if it's been reflected. Well, a sine graph normally goes up, right? So it normally starts by going up from the midline. If this were going down, like if it were instead going this direction, that's how we would know it was reflected. So this one has not been reflected at all. The amplitude is the distance from the midline to a peak, right? So if I look here, I can draw in that distance and then just count it out, right? So 1, 2, 3, 4. So we have an amplitude of 4. And don't forget that the amplitude is always a positive number, right? It's a distance, so it's never going to be negative, all right? Now, the period of our graph is the horizontal distance it takes to complete one cycle. So this is where I like to grab my highlighter and just highlight one cycle of sine. So remember, sine goes up, it comes back down, and then it comes back up to the midline. So this is what one cycle of sine looks like right here. And then I like to trace in the horizontal distance that is covered, right? So it starts here, ends here, right? So this is the horizontal distance that it travels in one cycle. So it goes from 0 to 2 pi. So the period is 2 pi. All right, so now if I want to write my equation for this thing, we start with our template, right? So we say y equals a times sine x plus h, or plus k, right? The h would normally go in the parentheses, but I told you I'm not going to give you anything with a phase shift on this test, so we don't need to worry about the h value. It's always going to be 0. But we do need to make sure that we put the amplitude in our equation and the midline and whether or not it's been reflected. Right, so these pieces, the a and the k values, we actually found those already. Okay, so I'm going to go ahead and write my equation. We're going to say y equals, remember our amplitude here was 4, so I'm going to say 4 sine x. Right, so we got 4 sine x. We knew it was a sine function. And then the midline, right, this is where our midline is. Okay. This is our amplitude. You see, it's all that work that we did finding all that other stuff were actually the things we needed to write our equation. So this midline was right here at -1. So that means I need a -1 on the end of my equation. And that completes my equation. Okay. All right, let's do one more problem here. This one is asking us to graph y equals 2 sine x minus 3. All right. And the way that I had shown you to do this in previous videos was to just start by graphing regular old sine, right? Or if it were cosine, you would graph normal cosine. Before it was transformed at all, before it was stretched or shifted up or down or anything like that, just graph the regular sine or cosine. So we're going to start with regular sine. And so remember sine, so we would think, okay, well, sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, 3 pi over 2 is at -1, and then the sine of 2 pi is back at 0. And then we get our wave. Okay, So this is what our wave looks like before we do any of the transformations. All right, and then what you want to do is you want to go and read your equation. All right, so we notice this thing has an amplitude of 2 and it has a midline of -3. So this is going to shift down. If I'm writing out what's going to happen to this thing, okay, we're going to shift down 3 and then we're going to stretch by 2. Okay, so those are the two things that have to happen. So I'm gonna get my pen here. Let's do green first, and I'm gonna do the stretch first. And it doesn't matter which order you go in here, you're gonna end up with the same wave. So I'm gonna start with the stretch, and remember the way that we stretch is we go to each individual point and we look at the y value, and then we multiply that by 2, right, or whatever the stretch factor is. So since this one is 0, 0 times 2 is 0. So that point's gonna stay right where it's at. This one is at 1, so 1 times 2 takes us up to 2. This one is at 0, so it's going to stay put. This one is at -1, so it goes to -2. And this one is at 0, so it stays at 0. Okay. And then we draw our new wave. Okay, so there's our stretch. We have our stretch done. Now we need to move this thing down 3 units. So now we are working with the green wave, and the green wave needs to go down 3. Let me grab a different color here. And the way that we move something down 3, we just go to each point, and then we just physically move it down 3 units, right? So if this one's at 0, it's going to go down 1, 2, 3. It's going to end up at -3. This one is at 2, so it's going to go down 1, 2, 3, so it'll end up at -1. This one's at 0, so 1, 2, 3. It ends up at -3. This one is at -2, so 1, 2, 3. This one ends up at -5. And then this one is at 0, so 1, 2, 3. There we go. So now we have our 5 points. All I got to do now is just draw my final wave. And there we go. So this would be the one that we end up with when we do both transformations. All right, guys, that's it for today's review. If you have any questions, make sure you let me know. If any of these topics were a little bit confusing, don't forget that you can go back to the previous lesson videos where I give more in-depth explanations on things in those lessons. So if you feel like you need a little bit more depth to the explanations, feel free to visit those previous videos that we've done or ask me questions in the Zoom chat. All right, guys, have a great day.